Imagine you're staring at the night sky, just another ordinary evening, and suddenly a star blinks. Not just once, but in two quick, identical flashes. Then silence. Nothing. For years. Until one day it happens again. Somewhere else. Another star, another double blink. No explanation. No confirmed pattern. No clear source. Welcome to the strange and captivating world of Optical SETI, where we're not just listening for alien radio transmissions, we're watching the stars, and the stars might just be blinking back. More than 6 decades ago, the search for extraterrestrial intelligence, SETI, began with a project called OUASMA. Frank Drake, the man behind the Drake equation, pointed a radio dish at a couple of sun-like stars, hoping to catch a whisper from across the galaxy. Since then, scientists have tried everything: radio, infrared, microwave, even laser pulses, to answer the same old question: are we alone? And while the answer has remained elusive, it's never been boring. Fast forward to today. Richard H. Stanton, a retired NASA engineer who's worked on legendary missions like Voyager and Grace, has been quietly running his own SETI campaign from the Shea Meadow Observatory in Big Bear, California. No fancy NASA lab, no billion-dollar budget, just a 30-inch telescope, a custom-made photometer, and thousands of hours of watching the stars. Stanton isn't listening. He's watching, and not just any watching. He's sampling starlight every 100 microseconds with a technique called photon counting. The idea? If someone out there is trying to communicate with laser pulses, brief, powerful blips of light, they might be visible, even across light years. And then came May 14, 2023. While monitoring a star called HD 89389, about 100 light years away, slightly bigger and brighter than our sun, Stanton's system picked up something strange. 2 fast, closely matched pulses of light, 4.4 seconds apart. The signal didn't look like a satellite, or a meteor, or a plane. It didn't match anything he'd ever seen. The star got brighter, then dimmer, then brighter again, all within 0.2 seconds. That's not typical stellar behavior, not from an object millions of kilometers wide, and not without a very specific cause. Stanton did what any good scientist would do. He tore the signal apart, checked it against known sources of interference: atmospheric noise, birds, satellites, cosmic rays. Nothing matched. Even more bizarre, when he compared the 2 pulses, the fine structure, the tiny variations in light between the peaks, was nearly identical. It was like the star stuttered, then repeated almost the exact same stutter 4.4 seconds later. And this wasn't the first time. Back in 2019, while observing HD 217014, also known as 51 Pegasi, home to one of the first exoplanets ever discovered, Stanton had caught a similar signal, dual pulses. At the time, he dismissed it, thought it might be birds or instrument noise. But now, with HD 89389 showing similar behavior, that's at least a possible pattern. And patterns, if confirmed, can mean everything. Then in early 2025, it happened again. A third event, a new star, HD 251, 81 light years away. 2 pulses, same structure. 3 events, 3 stars, years apart, yet all showing the same strange double blink. So what is it? Natural phenomenon? Some weird trick of light? Stanton isn't claiming it's aliens, and who could blame him? Science is full of false positives, but he's also not dismissing the anomaly. Because here's the thing: whatever caused these pulses, whatever modulated the starlight, it might not be coming from the stars at all. In fact, based on timing and structure, it could be closer, much closer, possibly even within our own solar system. Some possibilities Stanton considered include atmospheric refraction, maybe shock waves bending the starlight just right, Or maybe some kind of object passed between us and the stars, diffracting the light. Could it be a satellite we haven't cataloged? An asteroid? Each explanation has problems. None fully account for what was observed. And that's the unsettling beauty of it all. We want answers. We crave explanations. But sometimes space throws a mystery in our face and whispers, "Not yet." Stanton's work is part of a growing interest in optical SETI, using light instead of radio to search for intelligent life. It's cheaper, faster, and in some ways more precise. Projects like Laser SETI and Breakthrough Listen are also exploring this frontier, scanning the skies for patterns, flashes, anomalies. But Stanton's method stands apart. He's not sweeping the sky, he's locking on, one star at a time, watching like a hawk. And maybe, just maybe, that patience is starting to pay off. He's calling for more data, more eyes on the sky. He suggests arrays of telescopes synchronized across vast distances. If something is moving between us and the stars, these setups could reveal its speed, direction, even size. And if the star's light is being modulated without anything passing in front of it, well, that opens the door to a very different kind of question. As of now, Stanton isn't making wild claims. He's not saying it's aliens, but he's not saying it's not aliens either. And maybe that's the most honest answer we have. Because in the vast silence of space, it's the rare, unexplained pulse that reminds us someone or something might be out there, blinking, waiting, watching us back.
It's the year 1977, and astronomers are stunned. They've just picked up a bizarre and really powerful radio signal coming from the direction of the constellation Sagittarius. The signal shockingly matches the frequency of neutral hydrogen. What's the big deal? This is the very frequency many astronomers believe might be used by extraterrestrial civilizations trying to communicate. Since then, the signal has become legendary in the search for extraterrestrial intelligence, aka SETI, community. But what exactly was that mysterious signal? To understand this, let's go back to the 1970s when the Ohio State University Big Ear Radio Telescope was active. For more than 2 decades, from 1973 to 1995, it played a major role in the university's SETI program. By the way, it was the longest-running SETI project in history. And in 1977, Big Ear detected something extraordinary, the WOW signal. This wasn't just any signal. It was a strong narrowband radio signal, right near the important neutral hydrogen frequency. The Big Ear telescope might be gone now, but the mystery of the WOW signal still fascinates scientists today. Imagine this. You want to tell an extraterrestrial civilization about humans. How would you describe our average height? We can't use feet or inches because these units mean nothing to them. Even here on Earth, we don't all use the same measurements. To communicate with other civilizations, we need a universal way of conveying information. Luckily, the emission of light by matter comes from an electron jumping between quantum states in an atom. This process, governed by quantum mechanics, results in specific and fixed radiation frequencies and wavelengths, no matter where you are in the universe. Since we believe the laws of physics are the same everywhere, these wavelengths are universal. This makes them a perfect standard of measurement that any civilization could understand. For example, on the Pioneer spacecraft's gold plaque, we used a particular wavelength as a unit of length to describe information about humans and the spacecraft's origin. So, if an extraterrestrial civilization wanted to talk to us, they could have used the frequency of the WOW signal. And that's pretty amazing. The signal lasted the entire 72 seconds that Big Ear was tuned in. A few days later, astronomer Jerry R. Amon was looking over the data when he spotted the unusual signal on a computer printout. He was so surprised that he wrote WOW next to it, and that's how the signal got its famous name. The signal also has another, not so exciting name, 6EQJ5. Some people thought it might be a hidden message, but it actually just shows how the signal's intensity changed over time. The WOW signal sparked all kinds of theories. Some people believed it was a sign of extraterrestrial life, while others were sure that it was some interference from human activities. There were those who believed it could be a natural phenomenon we didn't understand yet. New research seems to have finally solved the mystery, but there's one thing we'll talk about a bit later. First, let's get into detail. A team of scientists, led by Abel Mendez from the Planetary Habitability Laboratory at the University of Puerto Rico at Arecibo, revisited the mystery using data from the now-closed Arecibo Radio Telescope, collected between 2017 and 2020. These observations were similar to those made by Big Ear, but they had better sensitivity, resolution, and polarization measurements. Arecibo detected signals similar to the WOW signal, but there were some important differences. These signals were less intense and came from multiple locations. The scientists believe that these signals, including the original WOW signal, can be explained by natural events in space. Their theory sounds like this. The WOW signal was likely caused by a sudden brightening of hydrogen due to a strong, short-lived radiation source. It could be a Magnetar flare or a soft gamma repeater, SGR. A Magnetar is a neutron star with a way stronger magnetic field than ordinary neutron stars. And an SGR is an astronomical object which emits large bursts of gamma rays and X-rays at irregular intervals. In any case, such events are pretty rare and depend on very specific conditions. But they can cause hydrogen clouds to light up for short periods. According to the researchers, what Big Ear picked up in 1977 was one of those bright hydrogen clouds in its line of sight. The study suggests that the signal's rarity can be explained by the precise alignment needed between the radiation source, the hydrogen cloud, and the observer. It means that the WOW signal may actually be the first recorded instance of an astronomical maser flare in the hydrogen line.
This signal had been traveling through space for 200 million years, and now, when it finally reached Earth, it brought a fascinating story with itself. It might even help us solve an 18-year-long mystery. We caught this one in 2022. It was such an intense burst of radio waves. Even though it lit up for a fraction of a second, it outshined entire galaxies. At first, this signal hasn't caught attention because we've seen similar things before. It was a fast radio burst, or FRB for short. These guys have been a mystery for years now, all because we have no idea where they come from. Now, FRBs are brief booms of energy coming to us from all over outer space. They're barely catchable, lasting up to 3 seconds. But they're also very hard to miss, because their power is absolutely unimaginable. One little burst can release as much energy as the sun does in an entire day. They've been a puzzle for us ever since 2007. We've caught over 1,000 of those signals from literally everywhere, from our own galaxy to places as far as 8 billion light-years away. And none of them revealed where they're coming from or what they mean. At least we know they're not from extraterrestrial creatures. They have to be coming from something that happens nearly constantly, and this recent signal might finally help us learn the truth. It lasted about 2 milliseconds, and it wasn't particularly bright. But when researchers took a closer look, they realized they can actually finally track this one. They got to it immediately. They saw that the burst came from a galaxy about 200 million light-years away. In other words, this is exactly how long these radio waves have been traveling to us. The signal flickered in a weird pattern. This is what we call a scintillation. When light or radio waves travel to us, they can stumble upon unexpected crazy clouds of gas. The particles in light waves start bouncing off this gas, which disturbs the signal a little bit. So when we received it, it was a bit weird and distorted, kind of like me. But this exact cloud was what helped us locate where exactly this signal came from. Turns out, it came from a neutron star. Now these are some fascinating guys. They're the remnants of stars that live fast and burn bright. When a powerful star like this, much larger than our Earth, runs out of fuel, it can no longer support its weight. So it goes away with an insane spectacle called a supernova. During its last moments, its core collapses under its own super-strong gravity, and this creates one of the densest objects in the universe. Again, a lot like me. Hey, what can I say? For curiosity, let's compare it to osmium, the most dense element on our planet. If you had a small cube of osmium, it would weigh around 0.8 pounds. That's already pretty heavy, and it means that 1 cubic foot of osmium would weigh a shocking 1,410 pounds. That's like an average cow. Now, just try to guess how much a small cube of neutron star would weigh. Wrong. It would be a horrifying 7 billion tons per one little cube. Don't even think about holding it in your hand. That thing would warp the fabric of reality around it. It's kind of like trying to imagine Mount Everest being squeezed into a tiny ball. Hard to even imagine. So, even though they're so heavy, these stars are surprisingly small, only about 6 miles in radius. That's like a city size, and it would still weigh more than our Sun. But if that's not enough horror for you, the neutron star we're talking about wasn't your regular one. It was a magnetar. Now, magnetar is a rare type of neutron star. When a neutron star is born, there's only a 10% chance that it will become one of those guys. It can happen if, while the star is collapsing, its magnetic field grows wildly stronger. The spin is rapid, the insides are going wild, and boom! We've got a magnetic field 1 trillion times stronger than Earth's. More than that, these are among the most extreme magnetic fields in the entire universe. They can literally rip atoms apart. Which is exactly what they do. They just rip everything apart. So they end up being surrounded by a super hot, electrically charged soup of particles called plasma. The magnetic field is going wacky, twisting, and bending the plasma as it sees fit. And this all just ends up as an ultra-hot party. Everyone is constantly colliding, scattering, and being absorbed. Not the best place for a hangout. Now, back to our main character. The magnetar in our story also had a plasma soup and a terrifying invisible field surrounding it. And this is exactly where that mysterious signal came from. A signal was born somewhere in that place, at a distance of 6,200 miles away from the magnetar. Sounds like a lot, but that's a distance shorter than a flight from New York to Singapore. But this is very weird, because how can a radio burst even escape a place like that? Now, usually they'd end up being blocked or absorbed. Most often, radio waves end up hanging out there like in a cage. This one, however, managed to break free somehow, which means that something happened that punched through the plasma. Energy somehow goes goofy, twists and reshapes itself in such ways that it starts releasing radio waves. Now, in any case, this means that FRBs most likely come from neutron stars and various types, like magnetars or pulsars. Recently, astronomers made a new amazing telescope called CHIME, the Canadian Hydrogen Intensity Mapping Experiment, a mouthful. This one detects FRBs literally every day. FRBs are full of surprises in general. In the same year, we discovered an FRB with periodic peaks lasting over 3 seconds, much longer than typical bursts. This one could also come from a neutron star. But if it was just neutron stars, we wouldn't probably receive them all that often. It looks like these signals are very diverse and might actually be born from all sorts of places, like near black holes. So there are some other theories about their origin. For example, they could come from 2 stars smashing into each other. What could be more epic than that? A collision of 2 stars would release unimaginable energy, and they destroy each other completely. Uh-oh. Some astronomers think they could explain FRBs, but of course, that's not something that happens often at all. Also, FRBs sometimes repeat. Most of them flash once and disappear, but sometimes they almost flicker like the one we discussed. Some of them even follow very precise patterns. For example, one well-known repeater follows a 16-day cycle. It goes crazy for about 4 days and then goes quiet for 12 days before starting again. This one is hard to explain even with neutron stars. There has to be some unique astrophysical mechanism at play. Maybe something that orbits something else. But anyway, a star's collision would only explain signals that flash once and never again. Another possibility is the Pulsar. It's a goofy name for a very dramatic idea: a neutron star turning into a black hole. Once again, an event like that unleashes a huge burst of radio waves. But, again, an occasion like that would be incredibly rare, and the signals aren't supposed to repeat. Black holes themselves are a pretty good option, though. They're central to many FRB theories. Could these bursts come from a neutron star falling into a black hole? Or from a collapsing black hole itself? Maybe even dark matter interacting with a black hole? Hey, who knows? Let's just throw all the ideas in there. Of course, the thing that everyone's most excited about is extraterrestrial civilization. Maybe not all of these bursts, but at least some of them could be signals from our intelligent neighbors. But like we said, that's very unlikely, considering that the signals come from all over the sky and many different distances. Also, almost all of them are the same, and that would be super hard and weird from an intelligent civilization to try and reproduce. Though who knows what else we might discover in the future. We still can't find the source of the mysterious signal we've been receiving since 2018. We receive it every 22 minutes and nothing can explain this. Some scientists even believe it could be coming from another civilization we haven't met yet. This strange radio signal wasn't found by a scientist on a serious mission. It was actually discovered by a college student just doing a regular project for school. Tyrone O'Doherty, an undergrad student at Curtin University in Australia, was sifting through old data of the southern sky. He was looking for any weird blinking radio signals. He finally stumbled upon one from 2018 that seemed to shoot radio waves towards Earth like a lighthouse beam. Excited about his find, Tyrone shared it with his mentor, radio astronomer Natasha Hurley-Walker. She dove into researching this signal, hoping for a breakthrough. But despite checking different frequency data, they hit a dead end. But then, Natasha spotted a pattern. The signal repeated every 18 minutes. This was huge. But just as they were gearing up to study it further, poof! The signal vanished after only 3 months, leaving them with nothing. Not giving up, Natasha and her team scanned the skies again, desperate for a clue. Months passed, but nothing turned up. They were ready to give up, and then suddenly, a new signal popped up. This one kept blinking for 5 minutes, then it disappeared. And then it came back exactly 22 minutes later. The main question was if that signal was related to an 18-minute one. To figure it out, Natasha went back to the old radio data from that area. As they dug deeper, they realized that, yes, and these signals aren't anything new. They've been beaming towards Earth for 35 years. Back in 1988, Indian and American telescopes had caught them, but they got buried under tons of other data. This was great news for space explorers because it meant they could now calculate how far away this mysterious object was. After doing the math, they figured out it was incredibly far, even on a space scale, 15,000 light-years from Earth. Now, the only thing left to uncover was what exactly this object was. Walker and his team started comparing it to all the known radio-emitting objects out there. Yet its source remains a mystery. The signals still pop up every 22 minutes on NASA screens, always ending with a frustrating match not found message. The scientists called it J183910. Some think that the signal might come from some extraterrestrial beings. Maybe it's the signal that SETI, the search for extraterrestrial intelligence, has been waiting for. This project has been working for over 50 years, trying to find any evidence of life beyond Earth. They also scan the skies for radio waves, laser pulses, and other mysterious signals. So maybe it's a way for extraterrestrial folk to communicate their location. While that idea may sound exciting, we need to be careful about jumping to conclusions. First, we don't have solid proof for that. Before any concrete evidence, it's just speculation. And also, there are other more plausible explanations. Most likely, it comes from a natural phenomenon, and there are a couple of theories for that. The first one is the pulsar theory. Imagine a huge star in space, much bigger than our Sun. Sometimes these big stars finish their life journeys in a spectacular event called a supernova. When this happens, the star's core collapses, becoming super compact, as if you're squeezing all the stuff from that star into a tiny space. That tiny, superdense core is called a neutron star. Some of these neutron stars are extra special. We call them pulsars. They get their name because they seem to pulse with energy, like a space lighthouse. These pulsars have incredibly strong magnetic fields, much stronger than what you'd find on Earth. They're like enormous magnets in space. Because of this, they shoot out beams of energy. They're also spinning super fast, so these beams of energy seem to pulse on and off as they spin around. Now, the strange signal we detected seems to have similarities with pulsars, but not quite. Pulsars usually have a predictable lifespan and slow down over time, eventually stopping their radio signals. In contrast, our mysterious signal is quite persistent and is blinking beyond what's expected for pulsars. So, maybe it's not a typical pulsar, or not a pulsar at all. There's also a magnetar theory. Now, a magnetar is another type of neutron star. They're like supercharged versions of pulsars, with even stronger magnetic fields and slightly longer pulsating periods. Maybe this is what causes our signal's intense persistence. However, when we plotted the data, we also realized the signal didn't match the magnetar's vibes either. Magnetars not only send out radio waves, but also powerful X-rays because they're so energetic. But the signal we received was only sending out radio waves. So we figured it's not a pulsar and not a magnetar. The signal's behavior is very strange and suggests an unnatural source. This means there might be something in the universe that scientists haven't fully explored yet. And there is a space object that we don't know much about. The final theory is the so-called dwarf pulsar. Sounds a little dopey to me. Couldn't help myself. Now, a dwarf pulsar is like a star that blinks with light flashes, similar to pulsars, but it takes longer for each blink. Usually, white dwarfs are the leftovers from smaller stars. They don't blink because their magnetic field isn't as strong as pulsars. But when a white dwarf becomes pretty hefty, almost the mass of our Sun, it gets super dense and starts pulsating with a strong magnetic field, just like pulsars. They have a cool quirk. White dwarfs are made of electrons, not neutrons like pulsars. When these charged electrons start dancing with a magnetic field, they shoot out periodic light flashes, which happen every 100 to 1,000 seconds. As you remember, our signal has a period of 22 minutes, 1,320 seconds. A bit longer than the usual white dwarf pulsars, but it's much closer to the truth. So far, this sounds like the most plausible explanation. But even this theory isn't fully confirmed yet. This just shows how much there is in the universe that we're still figuring out. For example, fast radio bursts, another mysterious type of signal we've been detecting. They're like quick, intense bursts of energy in the form of radio waves. They have a ton of energy. FRBs are so powerful that sometimes they can be brighter than entire galaxies. Now, imagine this. They release as much energy in a few milliseconds as our Sun does in 3 whole days. Wow! These bursts happen all over the sky with huge frequencies, although some have been detected with lower frequencies. Every day, we catch around 10,000 random FRBs in the sky. Some of them repeat, but most happen once and disappear forever. Unfortunately, most of them only last for a fraction of a second, and by the time their energy reaches us, it's 1,000 times weaker than a mobile phone signal from the moon. This is why, despite their brightness, there's still a lot we don't understand about them. We're still trying to figure out what causes these FRBs. They could be coming from different sources, like already mentioned magnetars, colliding stars, or even merging galaxies or white dwarfs. As these bursts travel through space, they pick up information about the cosmic environments they pass through, like interstellar gas clouds. It's very unlikely that FRBs are some messages from extraterrestrial beings, though. Not only because there are thousands of them every day all across the sky, but also because we know that the sources of these bursts must be incredibly energetic themselves. Our neighbors would have to have equipment stronger than entire galaxies for that. But the bottom line is, while all these signals are fascinating, there's still a ton to learn about them.
Imagine you could travel through the universe by hitching a ride on space dust, meteoroids, comets, or even rogue planets. Wouldn't it be incredibly cool? This idea is known as panspermia. It has captivated minds for centuries, but despite its appeal, it hasn't gained much popularity among mainstream scientists. Mainly, it could be because it doesn't explain how life originated and isn't easily testable. At the same time, certain events have reignited interest in the theory, even among skeptics. And one of such events was the appearance of the mysterious Oumuamua in our solar system in 2017. Oumuamua was a mysterious object that zipped through the solar system at an astounding speed. It was the first interstellar object spotted passing through our star system and the first detected hyperbolic asteroid, an object with an orbit not bound to the sun. Observations indicated that Oumuamua was likely to be a highly elongated cigar-like object. Overall, it was a very unusual object. Scientists couldn't quite pin down what it was. Some of them suggested it was a comet, others bet it was an asteroid, and there were those who thought it might be a chunk of frozen hydrogen. In April 2020, astronomers presented a new possible scenario for the object's origin. According to one hypothesis, Oumuamua could be a fragment from a tidally disrupted planet. If true, this would make Oumuamua a rare object of a type much less abundant than most extrasolar dusty snowball comets or asteroids. What made Oumuamua especially interesting to those who support the panspermia theory is that it was a visitor from another star system, so it was possible that it could have carried life across the galaxy. The idea of panspermia advances 3 stages: escape from a planet, transit through interplanetary space, and landing on another planet. Therefore, the Oumuamua hints that panspermia is possible. Recently, a new study titled "The Implications of Oumuamua on Panspermia" has seen the light of day. It was led by David Tsao from Thomas Jefferson High School for Science and Technology, an intern at Johns Hopkins University. The study explored how many objects like Oumuamua might exist and what characteristics they would need to transport life safely across the cosmos. The researchers considered different types of space debris, such as asteroids and comets, and estimated their potential to shield life from harmful radiation, particularly gamma rays from supernovae. If these objects weren't large enough, the intense radiation would sterilize any microorganisms hitching a ride. According to their findings, space debris made of materials like nickel or silicate could provide sufficient protection. But for a passenger to survive, they would need to have a minimum size of about 21 feet. The study also tried to estimate how likely it was that extremophiles organisms that can survive in extreme environments could have been delivered to Earth in this way. They calculated that roughly 40,000 objects of at least 33 feet in diameter could have impacted Earth during its first 800 million years. While this number might sound like a lot, the chances that Earth itself was seeded by panspermia are extremely low, less than 0.001%, according to the study. Interestingly, the researchers didn't just consider Earth as a recipient of panspermia, but also as a potential source.
If Earth or another habitable planet ejected life-bearing material into space, that material could, in theory, seed other planets across the galaxy. The study suggests that under optimistic conditions, up to 100,000 Earth-like planets in the Milky Way could host life as a result of panspermia. However, many factors remain uncertain. For instance, the number of rogue or free-floating planets in the galaxy could significantly affect the panspermia hypothesis. Hopefully, when we discover more about these planets and the overall density of interstellar material, we will understand more about panspermia. The scientists have also underlined that the conditions in the galaxy were different in the past. For example, during an event known as the Late Heavy Bombardment, the rate of impacts on Earth and other bodies in the solar system was 100 to 500 times higher than it is today. If similar events occurred in other star systems, the potential for panspermia would be much greater. Despite its allure, the panspermia theory remains a fringe idea in scientific circles, all because of the many unknowns and its speculative nature. But as we gather more data from projects like the upcoming Rubin Observatory's Large Synoptic Survey Telescope, which is expected to detect many more interstellar objects and rogue planets, astronomers will likely revisit and reassess this idea.
Most of those twinkling dots scattered across the night sky seem unreachable. But one of them is Betelgeuse, a star so enormous and nearby that you can see it with the naked eye. To find it, locate the first 3 big dots in the Orion's belt. A reddish star to the left is Betelgeuse. It's one of the brightest stars we can see from Earth, and it's just 640 light-years away. No big deal. Betelgeuse has a blue-white O-type star, which is one of the hottest types to exist. Betelgeuse was scorching hot, reaching temperatures of about 90,000 degrees Fahrenheit. Although that was back in the day, now it's an elderly star, and it cooled down to just 5,800 degrees. You know, vacation weather. Blue-white stars are absolutely massive and burn incredibly bright because they have loads of hydrogen fuel. But they have a price to pay for this glory. They burn through their fuel super quickly. As they age, they transform into red giants. This is exactly what happened to Betelgeuse. It burned through its hydrogen and started burning helium instead. This caused its outer layers to puff up like a balloon, turning it into a red supergiant and making it one of the largest stars out there. Now it's stretching over 700 million miles in diameter. Now it's about 1,000 times bigger than our Sun. If Betelgeuse replaced it, it would swallow up Mercury, Venus, Earth, Mars, even Jupiter. And its atmosphere would almost reach Saturn. But something strange has been going on. Betelgeuse spinning way faster than it should for a star of its size. Huge stars like Betelgeuse are expected to rotate slowly, but it suddenly started spinning at a rate of about 3 miles per second. Thanks to powerful radio telescopes, Betelgeuse's orange-red surface can be seen in detail. That's how we learned that it often changes its brightness. Sometimes Betelgeuse shines super brightly and then gets very dim. This happens about every 400 days. And recently, a telescope called ALMA, which is made up of many antennas working together as one, showed that Betelgeuse's surface seems to be moving unevenly. It's like one side is coming towards us while the other is moving away. But all of it might be a trick of light. Betelgeuse isn't as smooth as our Sun. Instead, it's super chunky. Its surface is like a boiling cauldron. It's bubbling and churning incredibly fiercely. Imagine giant plumes of hot gas erupting from its core, reaching the surface and then vanishing back inside. And these bubbles are bigger not only than the Sun, but Earth's entire orbit around the Sun. These bubbles also rise and fall super quickly, even faster than a spacecraft. And maybe this tricks our telescopes into seeing it spin faster than it really does. Some astronomers also think that Betelgeuse could have swallowed up another star, and this gave it a spin boost. But these are all just theories. Things got even more complicated when Betelgeuse dimmed once again, this time in a pretty unexpected way. What's interesting, it was discovered using a weather satellite. A regular telescope had a hard time seeing Betelgeuse clearly because of Earth's atmosphere. So they used a satellite that normally watches Earth's weather, but can also take pictures of space. As we mentioned, it usually brightens and dims about every 400 days. But recently, it suddenly dimmed by 2.5 times more than ever before. This event got the name the Great Dimming. The first theory said that Betelgeuse cooled down and sneezed out a bunch of material, creating a massive dust cloud. This cloud blocked the view of the star, making it look much fainter than usual. They also noticed something strange happening to that dust. It started behaving differently, which might be a sign that something deep inside the star was causing trouble. Betelgeuse's brightening and dimming cycle now happens faster in just 200 days instead of 400. And to add to the mystery, in the spring of 2023, it started shining even brighter than it normally does at its peak. Why is this frightening? Because Betelgeuse might be preparing for its grand finale, and this wouldn't be very good for Earth. We might be on the verge of a supernova. When massive stars like Betelgeuse run out of fuel in their cores, they start burning different elements like carbon, oxygen, and silicon. Eventually, they end up with iron in their cores. At that moment, everything changes. Adding helium to iron doesn't produce energy like other reactions do. Instead, it sucks up energy. This causes the star's core to collapse, leading to what's called a core collapse supernova. A spectacular, breathtaking show. Supernovas are so bright that they can outshine entire galaxies. But a Betelgeuse supernova would be special. Because it's relatively close to us, it would be so bright that we could see it even during the day. When it happens, Betelgeuse will shine as brightly as a full moon, but all that light will be concentrated in one point. For about 2 months, it will be so bright that you could read a book just from the light of the supernova, even if you turned off all the city lights and had a clear sky. The idea of witnessing Betelgeuse explode as a supernova is truly thrilling. After all, the last time a star went supernova in our galaxy was way back in the time of Johannes Kepler, more than 4 centuries ago. That event, known as the SN 1604 or Kepler supernova, dazzled the sky for weeks. But don't get too excited yet. We're not sure when exactly it'll happen. One study says that the star might be in its carbon-burning phase. If we're near the end of that stage, then Betelgeuse might blow up very soon, during the next tens of years. But it's nearly impossible to determine because during that last phase, the star barely changes at all. Even though Betelgeuse is close enough for us to study its surface, we can't peek inside its core to see what's really happening with it. We might as well be at the beginning of the carbon-burning phase, and in that case, we might have to wait 1,000 more years before that cool supernova. Another study says that Betelgeuse might have less than 300 years of fuel left in its core. They say that Betelgeuse is known to expand and contract regularly, and its pulsation pattern hints that Betelgeuse is much larger than we previously thought. This would suggest that the star is further along in its life cycle and closer to going supernova. Other guesses come from observations of similar stars. For example, a star called VY-CMA in our galaxy is thought to be closer to going supernova than Betelgeuse, and it's been dimming steadily over the past century, unlike the relatively stable Betelgeuse. If Betelgeuse was about to go supernova, it would dim steadily and very quickly. Also, historical records suggest that about 2,000 years ago, people saw Betelgeuse as yellow, not red. If that's the case, then we might be in its early last days after all. In other words, we have no idea whether it will go supernova tomorrow or in 1,000 years. We just gotta wait and see. But let's say it goes supernova tomorrow. What happens to us then? The 1987 supernova in the Large Magellanic Cloud showed that the effects from the supernova might be so strong we can sense it even from very far distances. The Large Magellanic Cloud is almost 170,000 light-years away, and we still detected the radiation. It's kinda hard to say exactly what the danger zone is. A rough estimate could be around 100 light-years. Luckily, Betelgeuse won't pose any danger to humans. It's hundreds of light-years away, and its supernova won't influence us in any way. We'll be able to enjoy its supernova beauty without any harm.
Now see here, astronomers have recently discovered a neutron star, also known as a dead star, spinning at an extraordinary speed of 716 times per second. It makes it one of the fastest spinning stars we've ever found in the universe. And it's not just about its speed. The surface of this neutron star is erupting with super powerful explosions almost non-stop. But before we dig deeper into the mystery of this neutron star, let's figure out what these stars really are. They form from the remnants of massive stars that are at least 8 times the mass of the Sun. When such stars exhaust their nuclear fuel, they can no longer counteract the force of gravity pulling their matter inward. This leads to the collapse of their cores, triggering a massive supernova explosion that blows away the outer layers of the star. What's left behind is an ultra-dense core. That's a neutron star. These stellar remnants are incredibly small, typically just 12 miles wide. At the same time, they pack in more mass than the Sun. The density of neutron stars is also overwhelming. Imagine taking the mass of 2 suns and squeezing it into a sphere about the size of a city. A single teaspoon of neutron star material would weigh around 10 million tons. That's the same as the combined weight of 85,000 blue whales. Such an extraordinary density is what gives neutron stars their immensely powerful gravitational fields. When matter falls onto a neutron star, it accelerates to speeds of millions of miles per hour before slamming into the surface. The energy release from such impacts is truly astonishing. Now, despite its name, inside a neutron star, there are not only neutrons. A few protons survive down there too. Now, normally, protons repel each other since they have the same positive charge. But in a neutron star, that crushing gravity forces them so close together that the strong nuclear force takes over. It pulls them toward the neutrons like they're all part of the same team. Inside the star, things get stranger the deeper you go. Near the surface, neutrons clump into blobs, kind of like a neutron gnagi. A bit further down, these blobs link together into long chains, forming what scientists call the spaghetti layer. I'm getting hungry. At even greater pressures, the spaghetti chains fuse side by side, creating flat sheets. Think neutron lasagna. Keep going any deeper, and the lasagna eventually breaks down into a uniform mass. But even then, the structure isn't smooth. There are gaps, long tube-shaped voids that look a lot like penny pasta. So inside a neutron star, you've got layers of gnocchi, spaghetti, lasagna, and penny pasta. And each of them represents the mind-bending results of physics under insane pressure. Okay, I'm definitely having Italian for lunch today. Now, the recently discovered neutron star is part of a binary system located in a dense star cluster. This cluster is situated near the center of the Milky Way galaxy, approximately 26,000 light-years from Earth, in the direction of the Sagittarius constellation. The record-breaking spin of the star is extraordinary. If we take a period of not a second, but a minute, it'll be over 42,000 revolutions per minute. At the same time, the newbie ties with another neutron star, which spins at the exact same speed. Such extreme rotation rates are rare and make these stars cosmic outliers in terms of behavior and properties. Oh wait, we can't but mention our neutron star's binary partner. It's a white dwarf, a dense remnant of a star similar in size to our Sun. This white dwarf is pretty fast too. It orbits the neutron star once every 11 minutes. This makes the couple a binary system, with the shortest orbital period ever observed. Imagine a stellar object zipping around its partner faster than the time it takes to prepare a cup of coffee. Yep, that's the kind of speed we're talking about here. This tight, rapid orbit shows how powerful gravitational forces are inside the system. So you might be wondering what makes neutron stars spin so rapidly. It's something called the conservation of angular momentum. Let me explain. When a massive star collapses into a neutron star, it shrinks dramatically. Such a rapid compression gives an instant boost to its spin. It's like an ice skater spinning faster when they pull their arms inward. And the smaller the star gets, the faster it spins, which results in extreme rotation rates. In binary systems like this one, neutron stars can achieve even faster spin rates. Their trick is to steal matter from their companion stars. This process is called theft. No, accretion. The stolen matter carries that very angular momentum, which adds to the neutron star's rotation speed. The accreted material can also build up on the neutron star's surface, eventually. It triggers powerful thermonuclear explosions. They release immense amounts of energy, temporarily making the neutron star shine up to 100,000 times brighter than our Sun. It allows astronomers to study the intricate details of these extreme environments. NASA's X-ray instrument on board the International Space Station, officially called the Neutron Star Interior Composition Explorer and thankfully nicknamed NICER, observed 15 thermonuclear explosions on the surface of our neutron star between 2017 and 2021. One of those bursts displayed a unique pattern called thermonuclear burst oscillations. Those are highly asymmetric patches of brightness on the burning surface layers of accreting neutron stars. This pattern matched the spin rate of the neutron star and thus confirmed its extreme rotational speed. But wait, the best part is coming. While neutron stars are already extreme, there's another class of them that takes things to a whole new level – magnetars. Now, magnetars are neutron stars with unimaginably strong magnetic fields, up to 1,000 trillion times stronger than Earth's magnetic field. These fields set them apart from other neutron stars. They can distort atoms in nearby objects, making life impossible anywhere near them. As for the energy density of a magnetar's magnetic field, it's so high that it's 10,000 times greater than the mass density of lead. Magnetars also produce bursts of X-rays and gamma rays that are so powerful they can temporarily outshine entire galaxies. These bursts are often triggered by star quakes, violent shifts in the magnetar's crust caused by their own magnetic fields. For example, a gamma-ray burst from a magnetar in 2004 was so strong that it disrupted Earth's ionosphere. It hit Earth, and it was so intense that several satellites picked it up. The SWIFT satellite, built specifically to detect gamma-ray bursts from across the universe, didn't just detect the blast, it got hit with so much energy that its sensors got completely overloaded. And SWIFT wasn't even facing the burst. The energy was so strong it passed through the spacecraft and still overwhelmed its cameras. If a magnetar was located as close to Earth as the Moon, its magnetic field would erase all credit card data on the planet by wiping the magnetic stripes clean. Whoa, that's the level of power we're dealing with here. Magnetars are extremely active, but for a relatively short time. Their intense magnetic fields decay after about 10,000 years. After that, they stop emitting strong X-rays and gamma rays. Astronomers think that there are at least 30 million inactive magnetars in the Milky Way galaxy alone. These silent cosmic relics are scattered all over the galaxy. Neutron stars and magnetars serve as laboratories for extreme physics. They allow astronomers to have insights into the behavior of certain matter under conditions you can never replicate on Earth. The incredible density of these objects helps scientists figure out what happens when protons and electrons get compressed together to form neutrons. This creates states of matter that don't exist anywhere else in the universe. These violent explosions on neutron stars and magnetars also play a critical role in the formation of heavy elements like gold and platinum. These elements get scattered all over the universe during these energetic events, eventually becoming parts of planets and stars and you and me. Oh, by the way, NASA's NICER instrument has played the key role in uncovering the mysteries of neutron stars. Its ability to detect X-rays with high precision allowed astronomers to study the rapid spin of the neutron star we've been talking about and the thermonuclear bursts that occur on its surface. So, what could be nicer than that? Now, it's been a long time since there was a supernova in the Milky Way. Over 400 years to be precise. So hey, we're long overdue. So here are the most likely stars to go boom if they haven't already. At the top of the list must be the Southern Hemisphere's star, Eta Carinae. Greek letters before the name of the constellation indicate the rank of the star's brightness in that constellation. Sir Edmund Halley, in 1677, recorded Eta Carinae as the seventh brightest star in the constellation Carina, Eta being the seventh letter in the Greek alphabet. It might not have looked very bright to Sir Edmund and his contemporaries in the 17th century, but modern studies of Eta Carinae estimate it's 5 million times more luminous than our Sun. Luminous is a technical word astronomers use. It doesn't just mean brightness. Luminosity refers to the total energy released at all frequencies. Eta Carinae releases 5 million times more energy than the Sun. Truly one of the whoppers of the Milky Way, Eta Carinae is 100 times more massive and 240 times larger than our yellow-white dwarf sun, Sol. Obviously, since it appears dim, Eta Carinae is pretty far away, about 7,500 light-years away. Yet even at this distance, if this star goes hypernova, it can still impact Earth's ozone layer, disrupt satellite communications, and harm astronauts. 159 years after Halley's observation, Eta Carinae experienced a nova-like explosion. It increased from a relatively dim star to become the second brightest star visible from Earth, but only for a period of 27 years. From 1836 until 1863, Eta Carinae was the second brightest visible star after Sirius, the dog star, and Sirius is only about 8 light-years away. Since 1863, aside from a couple of flare-ups, Eta Carinae has dimmed back down to its original brightness at magnitude 4.5. Now, astronomers owe us a small apology, which we don't expect to get anytime soon, for star magnitude nomenclature. The brighter a star is, or planet, or moon, the lower its magnitude. Thus, stars brighter than first magnitude are either zero magnitude or negative magnitude. The full moon, for example, is magnitude negative 13. A magnitude positive 4.5 star, like Eta Carinae, is quite dim as seen from Earth, but it's clearly visible in a night sky without light pollution or clouds if you live anywhere south of the latitude of Cairo, Egypt. 30 degrees north latitude is the farthest north you can see this star. Now, listen up. Eta Carinae is currently up to something. It's been brightening again and is now brighter than at any time since 1864. It's a complex situation. Eta Carinae is really two stars, Eta Carinae A and Eta Carinae, what's your guess? Oh, B. There's a third star nearby that's also interacting with the double star's dynamics. Now, without looking, I'm guessing it's named Eta Carinae C. Good guess. Blown out into two incredibly massive globes of gas that are expanding at 20 million miles per hour, Eta Carinae is, without a doubt, one of the strangest looking stars you'll ever see. Remember, it's located at a great distance of 7,500 light-years away from us. And if anything had happened to Eta Carinae in the last 7,500 years, like going hypernova, we wouldn't be able to see it, because none of Eta Carinae's electromagnetic radiation would have gotten here yet. Astronomers are keeping a close watch on Eta Carinae because it can go hypernova at any time. Or maybe it already did 5,000 years ago, in which case we'd only have to wait another 2,500 years to see it. Yeah, like I'll put it in my planner. Now, from a list of over 30 likely candidate stars that might go supernova, Rho Cassiopeiae is many astronomers' choice. Another Greek letter, Rho, is the 17th letter in the Greek alphabet. It means that Rho Cassiopeiae is the star with the 17th brightest apparent magnitude in the constellation Cassiopeia. Yet Rho Cass, a nickname, is only one of 7 known yellow hypergiant stars in the Milky Way. It's another whopper. To be seen at magnitude 4.5 from a distance of about 10,000 light-years away, Rho Cass must be a very large star, a hypergiant. Placed where the Sun is, Rho Cass would encompass the orbit of Mars. But it's still yellow. It's not a red giant star. Red indicates a cooler surface temperature. Rho Cass, as huge as it is still as hot on its surface as our Sun, or even a little hotter. That can only mean two things. Deep inside its core, Rho Cass is fusing atoms much heavier than hydrogen or helium. Plus, Rho-Cas is producing much more energy than a red giant star. In the year 2000, Rho-Cas erupted massively. It brightened by 2 orders of magnitude as it ejected 10,000 times the mass of Earth into space at 4 times the speed of sound. Astronomers detected the signature of titanium oxide in this eruption. This means that Rho-Cas is much closer to going supernova, or in this particular case, hypernova, than astronomers used to assume. Iron is just a few steps above titanium in the periodic table, and when iron forms, fusion stops and a star collapses. Rho-Cas is really close, or more correctly, was really close, because the eruption we saw in the year 2000 really happened 10,000 years before. Many astronomers think Rho-Cas has already gone hypernova, formed a black hole, and doesn't even exist anymore. Meanwhile, Betelgeuse caught everyone's attention not so long ago, the star, not the movie. It dimmed dramatically, appearing only 37% as bright as it usually is. Is it getting ready to go supernova? Betelgeuse is by far the brightest star in the whole sky, in infrared light. This is an important fact because it relates to Betelgeuse's status as a supernova candidate, as we shall soon see. Betelgeuse is also named Alpha Orionis, another Greek letter designation. So we should conclude that Betelgeuse is the brightest star in Orion, right? Wrong. It's the second brightest star in its constellation. Rigel, or Beta Orionis, is the brightest one in that region. Figure that one out. It may be because Betelgeuse is classified as a semi-regular variable star, which sounds kind of redundant to me. Its approximately 400-day cycle of pulsation changes its brightness by about 1 full magnitude, going from much brighter than a first magnitude star to closer to a second magnitude star. But never was Betelgeuse observed to dim so rapidly or so drastically as it did recently. So what's going on with it? Well, from late 2019 to mid-2020, Betelgeuse went through a period of substantial dimming during a mass ejection event. The world astronomy community jumped on the situation, and in the course of their investigations, they came up with some surprising new factual data on Betelgeuse. First, Betelgeuse is not as far away as we once thought. The new, more accurate distance for Betelgeuse is 548 light-years. That's 25% closer than previously measured. The second new fact, Betelgeuse's diameter has been reduced by the same percentage. The star is now known to be 25% smaller than previously believed. The cause of Betelgeuse's dramatic dimming was also determined. The giant star ejected a cloud of gas that contained magnesium. The cloud blocked a large portion of the light coming from Betelgeuse and made it appear visually much dimmer than it really was. Magnesium is not halfway to iron on the periodic table, which means Betelgeuse is not as far along on the path to a supernova as was suspected previously. When iron starts forming in the star, it means that this star is close to shutting down its fusion reactions. The next step is implosion. We aren't quite there yet with Betelgeuse. This star emits most of its energy as infrared light, and it also indicates that its core is most probably still burning helium, and not something that would greatly increase the amount of heat, like carbon for instance. Betelgeuse will still go supernova, but not for another 100,000 years. So you can cross it off your supernova list for the time being. And as for how to correctly pronounce Betelgeuse, you can say it any way you like. There are as many different pronunciations out there as there are people who think they know how to pronounce it correctly. Now, supernova 1987A caught astronomers off guard when it lit up the large Magellanic Cloud 100,000 plus light-years away from the Milky Way. That's when attention was turned to a similar star much closer to Earth, Rigel, in the constellation of Orion. Could Rigel surprise us and suddenly go supernova? There's something called the supernova problem that you should, probably know about because it may relate to Rigel going supernova or not. It seems that stars over 17 solar masses don't always go supernova. Recently, a red giant star simply vanished. Once again, it didn't go supernova, it disappeared. This had often been happening in computer simulations of supernovae, and now it finally occurred in real life. Rigel's mass is 21 solar masses. In other words, it's 21 times more massive than our Sun. So, will Rigel go supernova or simply vanish into a black hole that it'll create in its core? Astronomers and physicists continue their work of learning more about the dynamics of massive stars, scouring the sky for the next supernova in the Milky Way. Meanwhile, we can rest confident that we on Earth are in no danger from the harmful effects of nearby supernova explosions. We live in a nice, quiet, peaceful stellar neighborhood, except for those Martians next door.